And so finding of roots of nonlinear equations, because previously what we did here, the solving of simultaneous algebraic equations, that also comes up most frequently whenever you are doing most of the time, means your material balance actually. So most of the time in material balance you got actually get algebraic equations actually. So those were linear algebraic equations. You could have non-linear also. So before doing that, actually we want to solve that how to find the roots of single nonlinear equations. So most of the time we are interested how to find the roots, and those have some important things. So in that category, actually you have these are various methods. Some of them you might know already. Actually, one is that you have a bisection method. One is your regular falsy or false position method. Other one is Newton-Raphson method, secant method, and then you have Mueller's method, fixed point iteration method. These are the some of them, not all of them actually. So let's see one by one what are those first. So first we see, let's say, a bisection method. So as you know, let's say you have a any equation, maybe a linear or a non-linear. So let's say you have a equation. So what the easiest possible way a person can do, just make a graph of that. So in hand, by hand, it is also a tedious job because you are necessary. You have to calculate at so many data points. Let's say you have just only one variable. Let's say you have you have several terms there. So sometimes you have maybe a fifth order polynomial, second order, third order, fourth order. So obviously you will have five terms, maybe maximum five terms could be present. So you need to calculate them, calculate several points and draw them and then plot them, how the trend is going on. But on computer, it's easy part actually. So let's say this is the one of the equation you have and you have just plotted it. So from here, you will come based on the nature of this particular graph actually. You can say it is intersecting one at this place. So wherever it is intersecting on x-axis, it is one of the root. Now, based on the nature of the graph, you will say the trend. From here, it is further going in this way. It may intersect again at some place. Correct or not?
Yes, sir.
Yes,
So
sir.
it may, from this nature, from there, we can say clearly that it will intersect at one more place. So that would be another route. So what the bisection, so plotting in plot command in all computational package tool is the easy command. It's because the time when we don't know what would be the root, how its behavior is, so it's easy to plot it actually. So plotting can easily can give what is happening inside this particular problem. Sometimes plotting is also not easy. It may be a complicated function also. So that depend on each. Sometimes you can plot it, sometimes you may not. So, but plotting would help. So from where it will help your solution that how close should I can take my guesses so that I can proceed further. So what the bisection do, you take the 2 points on the function such that one point will give the function value plus, other point should give the function value minus. So what does it mean? That at one of the end your function is coming positive, other end is coming negative. It means you have the root in between of two. Correct? Because a sign would only change once you are changing your coordinate system. Let's say you are in first coordinate here. Now you have moved to fourth coordinate. Only then your sign will change. Otherwise, your sign will not change. Correct or not?
Yes, sir.
Because your
Yes, sir.
function value is plus in the plus y side and minus in minus y side. So if you are going from first coordinate to the fourth coordinate or coordinate, only then your sign would change. So you will have root somewhere in between of that. Somewhere in between of that, you will have a zero value. So this is what the bisection do. Bisections means you guess the two values in such a way that your function value 1 plus should be a minus, other one should be plus. Now, next part, what they do that we want to proceed it further. So next way, so this is the starting philosophy of the bisection method. So let's say these are A1 and A2 are your two values, which you have guessed here, A1 and B1. Here function value is here. This is FA1 could be a some plus value. FB1 would be a some minus value, and then you have somehow you have the divided, taken the average of that. One this plus this divided by 2. So that would be another part here. So that's I will say how would you proceed here. So first part here, you take the two values in such a way that your sign of function should not match. Okay. Uh, I, I need to correct it 1 minute. It's not equal to so okay, so you have this, so such that your sign of function 1 and function 2 should not match. So those are your two perfect guesses. After that, again, each point, let's say first point, you have taken a guess fx1. You have to first check whether it's a function value. How much function value are you treating as a root or not? Because exact zero will not come. If exact zero is coming, it's okay, perfect answer. That's called an analytical solution. In numerical solution, exact zero will never come. So you have to give what function value can be treated as a root. Let's say 10 to the power minus 5 can be treated as a root, or let's say minus 4 can be treated as a root, or let's say minus 10 can be treated. Depend what function are you calculating. Let's say you have a function of money. In case of money calculation, money equations and that, root of 10 to the power minus 2 minus 3 doesn't make any sense, because the rupee value least value can be 1 rupee only. Yes or no? Correct?
Yes, sir.
So therefore, your tolerance cannot also be generalized, or function value cannot also be generalized. What function value can be treated as a root? That should be from your wisdom or analysis of the problem. Let's say you are calculating fugacity. So fugacity of gas is constant to the power minus 3, minus 5, something. So if your tolerance is just minus 5, you are totally doing error actually. Correct or not? So in that case, you have to define your tolerance based on your nature of the problem. So once you have fixed, let's say this function value can be treated as a root. So as you have taken a guess, so first you calculate what should be my function value at that. By chance, luckily your function value is coming same. It means your calculation is over. You need not to proceed further. This is the first and foremost rule. You have guessed some value, check your function value. If it is satisfying your criteria, that is your one of the root. If not, so you taken two values here, and both the values there are not can be treated as a function values cannot be treated as a root. Then check their sign. If they are not equal, then these are two perfect guesses for your bisection. Means you are now bracketing your root. Your root will lie in between of this point A1 or B, or there you have X1 or X2. So your root will lie in between of these somewhere. After that, next point you will calculate X3. It's just calculated by average of those two values what we have considered previously. Now you will again calculate the function value at point x3, and let's see whether it is a root or not. X3 is given, the function value at x3 is less than equal to given tolerance or not. If it is that, that's the root. Terminate the program. That is your root. So x3 can be treated as the root only. If not, then check the sign. If sign of fx1 is same as sign of fx3, then your x1 would be replaced by x3, and again you calculate a new value of x3. So x1 would be changed by x3, which you have calculated previously. So new x3 would be again your x3 plus x2 divided by 2. And this trend will continue, or by chance the sign of x1 means fx3 matches with x2. So the replace your x2 by x3. Getting the point?
Yes, sir.
Yes,
Right?
sir.
So you have to check the sign. X3 sign by chance fx3 signs matches with x1, fx1, then change x1 by x3, or you have the second choice would be that if it is doesn't match with that, so it will match with x2 only, fx2. So change the x2 by x3 and repeat the calculation till your function value satisfies your given tolerance, which can be treated as a root. So every time you are taking the average of that, and then you will keep on doing this. So previously you are at a1 or b1. Now you got the new choice is, let's say you got a2, then you moved here a3, then finally you would end up here. So now iterations, number of the iterations would depend that how far you have taken your guess. Somewhere here to too much far away. Let's say he has taken one value here, another value at that much extreme far end. So you have taken too much far away. So your iteration may take slightly more time. Someone might have guessed here a value somewhere here and this one, that A2 and B2 value. So he will move faster. He or she will move faster toward the root. So he or she will take less number of the iterations or trial. Sometimes, let's say you have gas value very close to the roots. So this completely a gas dependent. So it cannot be generalized that what number of trials or iterations you will take. Okay. So this is what your
Yes,
is
sir.
bisection method is. Next method is a regular falsi. It's slightly a advanced version of previous one. Previous one is the bisection one, which takes more number of the iteration as compared to any other method. But that's easy to program, easy to calculate. Just calculate function, replace it, and keep on doing. Only thing you have more of computational time. You will need more number of the iteration. But that method is always guaranteed to give you the root. That will never fail. Failures are not there. Okay, so now the means the another method is same as the previous one, slight change there. That you have guessed two values again same x1 and x2 here, such that your sign of function should be opposite. So it means you want to be here function value is minus, here function value is plus. So your root will lie somewhere here and there. What are they doing from that? They are drawing a line. This is your curve, this is your function red one. Now here x2 corresponding, you got a function value fx2 which can be treated as your y2. X1 corresponding function value fx1 which can be treated at y1. So you know the 2 points x1 y1 and x2 y2. Okay, so you can draw a straight line from these 2 points. So if you draw the straight line from these 2 points, so it may intersect somewhere on x plane. Yes or no? Right? So let's say this is the new intersection point x3. So practically you are writing here a equation of line which is passing from point x1 y1 x2, y2, and then you have a point xy, right? So because that's where you can write the equation of the line. Do you know which passes from line point x1, y1, x2, y2?
Yes, sir.
Yes.
So that is your y minus y1 equal to y2 minus y1 divided by x2 minus x1 multiplied by x minus x1, right? That's
Yes, sir.
your
Yes, sir.
equation of line passes from any 2 points. So in that case, here your x would change by x3, y would change by y3 or fx3. Now it is here the in this root in this means the method. Now your x3 is treated as a root. Okay. So x3, if you want to treat as a root, so corresponding value of function must be equal to 0 only. Yes or no?
Yes,
So
sir.
Yes,
same thing is being done here. If you are treating x3 as a root, therefore function fx3 must be equal to 0 to make it faster conversion actually. So in that case, this line would change here. So this will become here x3 would become x1 minus x2 minus x1 divided by fx2 minus fx1 and multiply by just fx1 only. So this is your new formula just to calculate your x3. Previously you have calculated based on the average. Here you have calculated based on the line, and the third point is being considered as a root that way. Now you got the new value of the x3. So x3, now you will do again same check whether the sign of the fx1 is same as the sign of the fx3. If they are same, then the change x1 by x3, else change x2 by x3, and again repeat the calculation. So in your final formulation, let me write it here actually. This I have not changed here. Let me, what happened to this? So this would be the equation which would be used to calculate your x3 actually. This would be your final equation, which will be used to calculate the x3. And again, procedure is same as the previous one. And each time you calculate your function value, check your the tolerance, and that would be treated as a root. Because finally, next point is the x3 here. Now you will draw the line between this point, let's say this point and this point. So you will come here, next point would be here somewhere. Then you will move here. Now next point would be somewhere here. So you are moving close to your this root, right? So you are moving at a faster rate as compared to the bisection one. So this is the another that's fine here. The in the regular falsy method.
yes, sir.
Yes, sir.
Okay.
Yes,
Yes,
sir.
sir.
So the next one here is the Newton the Raphson method. So previously you were guessing two values, and to guess the two values you are putting slightly more time because you are thinking that what should be the next value or guess so that my function value should be opposite or not. So you are thinking means slightly more as compared to the Newton-Raphson method. This say that you start from any value, just one guess, only one guess, but that should be correct. So that's what I wrote here, highly guess dependent. This is the only one If your guess is perfect, no doubt in a very faster rate, you will get a root. But if guess is not correct, then okay, you may not get the root also. But in previous one, you will never fail. That's the thing in those ones. This may fail at some place. But its conversion rate is very faster here. So what you have here, you have just, let's say you have taken a guess value x1, you got the corresponding value of function. From there, you draw the tangent. It will intersect on x-axis again. So you moved at this particular place faster. Now from here, you will reach to this point, again draw the tangent. So you are very fast. You see, you have taken a guess here, and within first trial, you are very close to the root. And next trial, you are further again close. You are moving a very faster rate close to the root. So if your guess is good, you will get the answer within few trials as compared to the previous one. So this is how you can drive this equation here, how this would come here. So you can draw here, you can find what should be your tan alpha. So tan alpha would be this B upon AC. So you can calculate that tan alpha, you can also calculate in terms of derivative of the function also. So this is just why do you calculate dy upon dx, the slope, right? Correct or not?
Yes,
Yes,
sir.
sir.
So therefore, this is your the dy in function value because from here to here AB, and this is your delta x here. So you move from here to here. So this is your the slope of the line only. So based on that, you got your equation of this particular point. So xi plus 1 would be xi minus fxi upon f dash xi. So this is your Newton-Raphson formula for just to calculate your function, your root actually. Same thing can also be derived from Taylor's expansion of a function fx plus h. Okay, so let's say you want to have a function of fx plus h. Your first function would be fx plus you have h, f dash h, right? Then you have h square f dash power 2 upon factorial 2 and keep on continue and neglect your higher order term. So from there you can find your h actually step size. So h would be fx plus h, let's say y times you are taking is a root. Hello, are you with me or not? आ रहा है समझ में क्या
Yes,
बोल रहा
sir.
हूँ? So,
Yes, sir. Yes, sir.
so
Yes, sir.
if you are taking that fx plus h is the x plus h is the root, so corresponding function value must be equal to 0, right? So fx
Yes, sir.
plus h is the root, so that side is the 0. This side you got fx plus h f dash x. So from there you will get the value of f dash x, right? h actually
Yes, sir.
h का value मिल जाएगा. So h value would be how much? It's this only, same thing. This is your h with minus sign. So your fx plus h is x plus h only. So this is your x, your h is coming this much. नहीं है तो मैं लिख के आपको दिखा सकता हूँ 1 मिनट में. Just if you just the recall it from here. So you can write a function here f x plus h. So you can write a Taylor series expansion of that. You will get fx here plus you will get here this h upon what would be here factorial 1 or just 1.
factorial 1.
Okay.
Yeah, 1.
या 1 कोई श्योर नहीं है.
Factorial, sir.
Sir,
फैक्टोरियल
factorial 1.
फैक्टोरियल होना चाहिए ना. So you will have here f for dash here. So where should I put f dash? This one. So f dash x here, right? I am thus neglecting a higher order term. So let's say if I considering this one that x plus h is a root, if I consider this as a root, so what would be my this side? Should be equal to 0. Yes or no?
Yes, sir.
So this side is coming equal to 0. So you can calculate from here that your 0 equal to this much. And from here, I will calculate what is my h. So h would be how much? So this minus of this one and divided by this one only. So this is your h. Now, what should be your x plus h now? X plus h would be your x plus this value only.
Yes, sir.
Yes.
Yes,
This is
sir.
practically
Yes,
you
sir.
can say you can denote it xi plus 1 and this is your xi. Correct? So that is the another way of the derivation of the Newton-Raphson method. Now, once you have this, so so we were here at Newton-Raphson part here. So you will only thing is a highly gas dependent part here. So if this is gas is fine, so most of the time, means you can say 95%, it will converge actually. Let's say what are the point of the failures. So let's say this is the again that how faster the conversion is. You have taken a route here. So you are moving in one trial you got here. This is first trial, second trial, third trial, fourth में आपके पास answer है. You got the answer, right? So this is initial gas, then first, then second, and third, fourth. You got the exact route. So that's the conversion rate is extremely fast here. Now, what about the failures? This type of nature, how would you come to know that what should I guess in all this? Now my plotting function, because you said that you have wrote a program and you wrote everything a correct program and still I'm not getting the root. So it happens that this is the oscillatory behavior of the Newton-Raphson method because each time you are drawing a tangent. So what happened here? So let's say this is your function, that this black one is your function, black line, black curve. This is your function, this one. Suppose a person has taken a first guess here. This is your first guess. Now, corresponding function value is the here. If you draw the tangent from here, it's going to this point. Now, from here, if you will reach the function, you will reach here. You will draw the tangent again. You are reaching again to the first point. So you are not coming out from a loop. Now you are inside a loop. So oscillatory behavior. From here, you got point 2. Now again from point 2, you reach to point 1. So you are moving. So while you are solving with the Newton-Raphson method or practically any computational method, you have to always put a check. The new calculated value of a root, or you can say new iteration, how much it difference from my previous one. Suppose it's not changing, I should do something. Correct or not?
Yes,
I
sir.
cannot keep on doing,
Yes,
let's
sir.
say I will put 100 iteration, or let's say some people would do the 1,000 iteration or 10,000 iteration, and you have put your program would continue because it will continue till your number of the iterations are there because you have not put any cross check there. So you may at last you will come to know that something is wrong with the program. It's nothing wrong. Yeah, some wrong is there in programming, but your main program which you wrote in command by is correct. So that need to be checked. At each trials, I should check what is my difference between the new calculated values and old calculated value of as a root, because each trial is a root only. Maybe it may be a perfect root or not. So you have to check. So in this case, by chance this is happening. So what you have to do, you have to push your root. You have to change your guess. So either you can double it or you can half it. Choice is completely yours. There are no straightforward rule for that also. So suppose you are in this case, so suppose you have taken this value, let's say x1. So you change your gas value, you may make it half. So if you want to make it half, you may move the somewhere here. So you may move here, you may come out of this loop actually, or decrease it or increase it. So because you want to get rid of this position. Okay. So this need to
Yes,
be
sir.
programmed somewhere in the programming also. If this kind of things happen, either I have to either double my gas or decrease my gas. So doubling, decreasing is the easiest, the nomenclature. So that thing need to be taken care for during for oscillator. This is one of the type of condition. Other behavior could be of this type. Let's say this is your function. ये blue line is your function. Okay. You are supposed to find a root of that. So what is happening? Suppose you have taken a position here. This is your guess. यहाँ पे आपने tangent draw किया. You went to this point. Okay, fine, good. Now you drawn the tangent here. You reach to here value of 0.5. So you are proceeding. You have the proceed to some point. Now let's see here. What happened after this? After this, it reached to the first point. Again is reached to here, again this way, so it will now keep on oscillating. It is now in a loop now again. Correct? So ये
Yes, sir.
दो ट्रायल के बाद लूप में चला जा रहा है and it will keep on continue. So you will not get the root here also. However, root is not there in between of this zone because root is somewhere here. Correct or not? So
Yes.
it is highly gas dependent in this particular sense. So right, so this particular zone is not at all good to give a gas. So somehow you have to come out to this side. So that only would be taken care while you are putting a check command, my function value, how am I proceeding? Am I proceeding? Am I diverging? Am I converging or not? Okay, so that need can be taken care easily in program. That's not a big deal. The means the another type of this thing, this pitfalls or you can say failures. Again, this one we have already talked actually. This is another condition here. This we have talked previously in the because we were here. ये आपने guess किया और now you have fixed up between these two conditions, x2 and x3. वो यहीं पे it will keep on circulating. So this is again no convergence here. Same thing here also. In this particular case also. So ये आपने गैस लिया, ये आपके पास में रूट था, राइट? दिस वाज द वन ऑफ द रूट. करेक्ट और नॉट? अब यहां से यू वेंट टू द न्यू पोजीशन बाय टेंजेंट. अब from here you have drawn the tangent somewhere, you moved the somewhere very far away here. So you went outside the root zone also. Correct or not? So आपका guess was really fine, but only because of this change the way, the method which we are taking, that has taken away from the root part completely out. Now you went somewhere outside. And there is no surety that you will come back to here. Because from here, tangent is going to again this side. So this way you will bend out from the solution zone actually. So you have to change your gas. So this you have to take care. Same thing here also. You have the here, now you went here, now you see here, यहाँ पे यदि आपने tangent ले लिया, तो आपका infinite में चला गया. अब ये कहीं x axis पे intersect कर ही नहीं रहा. You went in an infinite loop. And now you are thinking that you wrote the something a wrong program. You have not. This is the nature of your function, right? So therefore, sometimes it's easy to get it plot and just see what is happening, because you are finding a root just to take that value and use it somewhere else. This is not only your task. Yes or no?
Yes, sir.
In
Yes,
a
sir.
modeling
Yes, sir.
simulation, person or the engineer finding a root is not only the main task, it is the one of the very small component of some of the part. Major task is the something else. Design something, do something. It is one of the component. So if this is not getting solved easily, so you would be stuck somewhere. So it's easy to draw the first and take the trend of the graph and something. And sometime from the nature or from our practice, we already know the answer. Let's say we are calculating a Q line equation का root निकाल रहे हैं. So you know what would be the value of Q, correct or not?
Yes, sir.
और
Yes,
आप
sir.
एक जो है डिस्लेशन कॉलम में R minimum कैलकुलेट कर रहे हो, you are calculating a R minimum. So you know the maximum value, minimum value. So वहाँ पे based on practice, most of the time you know what should be my range of the answer. So that helped me. And sometimes, and it's better to plot it, just get rid of this part as early as possible. Fine. Now, next method is the
Yes, sir.
secant method. So secant method, here, once you have a Newton-Raphson method, this is from this you have, then you this is the easiest way of the derivative which we usually calculate. Actually the derivative is just a difference in delta y upon the delta x, right? That's why we calculate the derivative, correct or not? Normal derivative from first principle, correct?
Yes, sir.
Now from here you have the substituted the derivative in this equation 1. Now you got here another equation here, x1 xi plus 1 के लिए you got this another equation. You started from first value only, and then you got the another value from here. Now this says here you guess any two values. This method says you guess any two values, x1 x2, and start your calculation here. So this you say the guess any two value x1 x2, no matter what the sign is there, and you would always get the answer. So this is one of, you can say, the most powerful actually computational technique. Here no guess depend, just take any two value, just iterate it, and you will get the root. So this is also one of the good method. Bisection is, you can say, one of the best method, but it need more the iterations. So sometimes you have to compromise, you have to save your computational power also, right? So therefore, this method is one of the best one here. So this is the expression for that, just to calculate your new root value. I check your function value, and this is how it's the proceed here. The procedure is same. You have the point here, x1 and x2, draw here, you got the line from here, you got this particular point, again keep on drawing. This is a faster conversion in that particular way. Okay.
Yes.
So
Okay, sir.
can we come back here? Let's, okay, we will do in the next class. We have some time, the class time is over. So this is the another method here, Mueller's method. So we will cover it, but I would show you the problem so that you can do the something in this weekend something. So this is your one of the example here, multi-component flash mean the distillation. For that, this is the equation is given to you. I is number of the components you have. Here actually a number of the parameters. So here you have I equal to 1 to n. So here this ki and k, z and psi. This equation is given. Now here you have k, z and are treated as the parameter size unknown variables here. Now z is given to you. Z is given in this way for 4-component system. And k is also given to you that 2, 1.5 and zero point 0.5 and equivalent values. So you are supposed to calculate your value of psi by using the method which I have told you, bisection, regular false secant, Mueller's I have not taught yet, Newton-Raphson I have taught here. So okay, so by taking these values here, you just calculate here what should be the value of your psi. Okay.
Okay, sir.
Yes, sir.
Okay, sir.
Okay.
Yes, sir.
So you
Yes, sir.
try to solve it, and I gave the answer also from the my program is coming here 0.04344 something. So we will end here. Fine.
Okay, sir.
Okay, sir. Thank you, sir.
Okay, sir.
Thank you,
Yes,
sir.
sir.
Thank
Yeah.
you, sir.
Yeah.
Thank you, sir.
Yeah. Yeah. Welcome.
Thank you, sir.